Okay, so we have a mutated and solvated protein. We've done this beta-hairpin structure, and I've shown you how to mutate it. I've shown you how to solvate it in a sphere. And so now, if you continue forward with that, you should have the what I'm calling the wild type, the native structure that has no mutations on it. You should have that without water, with water, and you should have a mutation without water, with water. You can do as many of these simulations as you want to do. I don't know how much sense it makes to simulate them without water, but I'll show you what that process looks like. We have configuration files that load in structures. This is going to be a really fast simulation. I'm not going to worry too much about warming the structure up. What you can do is you can do a minimization first, and then you can ramp the temperature. If you were doing this for publication, you'd want to do things like that. But for a class activity, for the sake of speed, I think it's okay to just minimize the structure and then do the simulation. So this is a configuration file that will load in non-solvated structures. It's going to instantly go to 310 Kelvin, and it's going to put output files with the name 1le0_eq for equilibration. It needs to read in some topology charm files. It sets force field parameters. These are all just standard defaults that I'm using. I'm going to do a 2 femtosecond time step, and in order to do that, the rigid bonds needs to be set. You can go to shorter time steps and not have the rigid bonds, but again, for the sake of speed and running a quick simulation for students, I think this works well. Longevin temperature control, that just adjusts the speed distribution of your system, how frequently you're going to save information. Larger numbers tends to be better in terms of speed, but smaller numbers makes it to where you have more information at the end. There are spherical water boundary conditions here, but those are all commented out in this case because this is a non-solvated structure. And then I'm going to run 1,000 energy minimization steps, and then run 10 million simulation steps, which will give 20 nanoseconds worth of simulation. There are processes, and I've shown these in other videos, for checking whether or not the minimization has been effective. You can look at the energy minimization part of the simulation and make sure that it is asymptotic so that you're getting to your lowest energy structure. Same thing is true if you do a temperature ramp. You can look to make sure that everything is working well. For the solvated structure, it's all the same. I just have an underscore WS for water sphere, but everything else is the same, except we need a few extra parameter files for the water. And at the very bottom, we need to uncomment the boundary conditions, and it's important that you enter these boundary conditions from measurements on your solvated system. And I'll talk about that in another video. Okay, the number here is different, but when I run these, they'll all be set to the same number of simulation steps. Okay, so then what I typically do is just open, I'm working on Windows, I open a command prompt. I'm going to move into the directory where those files are, the configuration files are. And if I look at a directory listing, I can see that I have my structure files, PDB file, configuration file. The simulation's already been run, so it also has all the output files. But if I wanted to run it, I've installed NAMD3 and I've set my path variable. You can see how to do that in another video I have on YouTube. But I would just type NAMD3 and I would put my input le0 underscore eq dot config, and I would direct the output to something like le0, the same file name as the configuration, but I would add a log. And then I'd hit enter. This would run. Your cursor will come back when the simulation is finished. I'm not going to do that because I've already run these simulations. And so in the next video, I'll talk about what the output from these simulations looks like and how you can do some analysis.